Today we're going to take a look at project number 7. Project number 7 is the MPI project, Message Passing Interface, and this is how clusters of multiple computers are set up these days. This applies to clusters, this applies to supercomputers. Good thing to know. It's worth 120 points because it is a little more involved and it involves a brand new topic. Notice it's due on June 11th and no bonus days. Essentially, I've already given you the bonus days. If I don't start grading it or we don't start grading it the following morning, it's just not going to get done before grades are due. So yes, pay very close attention. There will not be ways of turning it in late. Okay, so we're doing something called autocorrelation. I like Wikipedia's definition of it is it's a correlation of a signal with a delayed copy of itself. Now, what in the world does that mean? It means we've got a bunch of random values. We put them on top of each other, and then we start shifting them. Okay, so here's zero shift, and we're multiplying them all pairwise. Okay, that'll be the sum of the squares, but then we shift one and we do the pairwise multiply again. Then we shift again, do the pairwise multiply again. What does that give you? If you start with a noisy signal, it really seems like just shifting it and multiplying gives you more noise, but it doesn't. What it gives you is if there's a sine wave buried in this random looking signal, it will tell you that, it will show you that. And that's what makes autocorrelation such a cool thing to try MPI on. Okay, so here is our original signal. Yep, it looks kind of like noise, but it's not. There are actually two sine waves superimposed in there. So here's what we'll do. We'll take array element 0 times element 0, 1 times 1, and so on. And, well, that's our sums element 0, 0 shift. We're not going to use this because, well, this gives you a very large number, and it's really just the sum of the squares. So, nope, we're not using it. But for the 1th element of the sums array, we're shifting it over 1. So we've got 0 times 1 and 1 times 2 and num elements minus 1 times 0. Notice we're wrapping around as we do this shifting. Okay, so now if the signal is truly noisy, there will be positive and negative values that are being multiplied together, and you add them all up, and statistically you're going to get 0 because there's a bunch of positives and a bunch of negatives. But if there's an embedded sine wave in there, you will not get 0. All right, now you shift over by 2. So we're going to fill the 2 element of the sums array, and we're shifting 2, we're shifting 2, we're wrapping around, shifting 2, wrapping around, shifting 2. And we do it again and again and again. Okay, we could do it the entire length of the array. We're not. We're doing it something called max shifts, which is 1024. Now, here's the trick. When you wrap around, like say here, yeah, you can handle that wrap around. Now you add 1 and you add 2 and you go, oh no, that goes beyond the end of the array. If that, then yeah, you can do an if statement, you can do a mod function. We're going to be even cleverer and simpler than that. We're going to take the first few elements out of the A array, and we're going to simply add it to the end. We're going to make the array bigger than it needs to be, and we're going to take the first few elements and put them here. And that way, when we shift by 1, we have now shifted off the end of the array, but we're not in we're not in illegal memory locations. We are, because we've added this extra max shifts out here. And then when we shift 2, we now have 2 that have shifted off the end of the array. So now we don't have to do any testing. We don't have to do any modding. Life is good. Okay. Now, when you get all done, when you graph sums, you're going to see a pattern. The pattern is the sine waves. Now, there will be a big sine wave and a little sine wave. We're doing harmonics. If you so measure the distance between the two large peaks, the two large sine wave peaks, that is the period, that distance of how many sums it took to shift over, that is the period of one sine wave. Then take the distance between the peak of a small sine wave and the peak of a big one. That is the other sine wave period. Just report those. You're gonna give us the graph, but report the numbers you get in your PDF report. Now, why do you do this? Okay, scientists and engineers use this to look for sine waves. Well, why would you do that? I've seen a couple examples of that. Here's one. There was a sensor cable that, because of where it was, it had to get strung under high power lines, big power lines on towers. And so there was a suspicion that the sensor data was being corrupted by 60 cycle hum from the big power lines. So they used that to go look for a 60 cycle sine wave in the sensor data. Also, I know the people who go look for intelligent life in the universe. If there's a random looking noisy signal from a distant galaxy, but if they were to find a sine wave in that, then that means somebody living in that galaxy has invented radio. And so that would tell them something kind of cool. So anyway, that's a use for this kind of thing. All right, the input data, and there's 8 mega values in the input data. There's two files. One is a text file, one's a binary file. You can pick, if you click on text, you can actually go see it. Well, there we go. Okay, yep, some positives, some negatives. Don't click on, well, click on the binary file if you want to download it. It won't let you see it. Okay, here's the size of the files. So if you get them and put them on your own system, yeah, this is how big they should be. Okay, if you were doing this whole thing without any kind of parallelism, this is what you would do for the number of shifts that you're allowing. We're going to do this. And again, I'm assuming we've added elements to the end. Okay, here's how we're going to do it in MPI. We're going to take all those number of elements, we're going to divide by the number of CPUs, and that's how much we're going to give each processor, except that we're giving them a little bit more. Again, we're taking into account the wrapping around. So we're going to give them a little bit more here, but that's how much we're going to give each processor. Okay. Yeah, I know what you're thinking. You're getting worried that you're going to do this sums plot and you're not going to see a pattern, or it's going to be kind of garbage with maybe a little bit of uniformity in it, and you're worried you're not going to see it. And don't worry about it. If you do everything correctly, it will be so obvious. It's like the graph reaches off the monitor and slaps you right in the face. Okay, you if it doesn't do that, then you've done something wrong. All right, so in the report, what do you think the two sine wave periods are? You're going to draw two graphs. One is showing performance, one is graphing these sums. Okay, and it shows this down here in your PDF. Show us your performance graph, show us the sums graph. Okay, you're going to turn in CPP file and a PDF file. Here's the skeleton code. And we're going to let the boss be node 0. Here are the two files. You're going to have to get them and put them in your area. This is the output file for doing the plot, because we're sort of plotting for two reasons. One, we are plotting or we are outputting performance, and two, we're outputting this signal that will reveal the sine wave periods. Okay, we're going to send the performance data to standard error, and we're going to send the plot data here. So you're going to really have two CSV files. Here's the number, 8 mega elements. We're only going to do the shifting 1024. We could do all 8 million shifts. We're not going to bother. We're only going to plot 400 sums points, and that's enough. That's enough to see the sine wave pattern. Okay, if you want to read the binary file, do this. If you want to read the ASCII file, uncomment this line, comment that line. Here's the globals. And here we are. So like all MPI programs, the first thing we're going to do is say in the -np space number on the command line, how many CPUs did I ask for? And then me, which one am I? And so from that, each processor will figure out what to do. And remember, this identical program wakes up simultaneously on all the processors. Okay, so you have to have this me value, otherwise you have no idea which one you are. PP size, PP stands for per processor. So per processor size is, well, we divide by the number of processors. We're going to create a signal for each processor that's that size, and normally that's all we would send, but here we're doing that clever max shifts so we don't have to do if statements and modding. We can just wrap around by continuing on. And here's where the summations are going to be. Okay, so if I'm the boss, I'm going to read a data file. Okay, and the other processors don't need to read the big data file because they're going to get pieces of it from the boss. Okay, so if you're doing ASCII text mode, here's what you need. If you're doing binary mode, here's what you need. Pick one. Again, it's only the boss that's doing that. The boss is also, if I'm the boss is also creating an array to hold the sums. And this is what you'll plot. Okay, we're going to start the timer. And we'll start the timer here, even though we're not computing yet, because we'll include the send time. So here is the boss gathering up its share of the data. Now, we could have the boss send to itself, but why? But the boss is grabbing its share, and it's going to compute as well. Okay, but we're just going to do a copy from the big signal to the boss's per process signal. Okay, now, again, if I'm the boss, I'm going to send to the non-bosses. So here we're looping through all the other processors. Oop, here we go. That's right. If this index is not the boss, then I'm going to send. The boss is going to do the send because only the boss gets to execute this line. And it's going to send starting here. This is an address. And it's up to you to look at the notes and figure out what goes in here. Okay, this is how each other processor is going to get it. Now remember, this same code wakes up on every processor. So if I'm not the boss, then I need to receive. And I'm putting it here. And yeah, you can figure out those arguments. Once I've got it, once all the processors have their share of the data, then they can do that. And we'll talk about that function too. But here we are. Now, once this function returns, that means the processor it's on has finished with what it's doing. So if I'm the boss, first thing I'm going to do is take my sums and copy them back into the big sums array. But if I'm not the boss, then I'm going to transmit my sums back to the boss. Okay, and remember, one of these arguments is the destination, the boss. Okay, now if I am the boss, then knowing that these things are on the way, I'm going to do a receive from a source, and I'm going to add that processor's sums into the big sums array. there we go. Stop the timer. Let's print some things. Here we're printing the performance data. Over here, we're printing the plot data. Okay, we're opening up that file and we're writing into it. So this will be a CSV file, which you can just double click on. And that's it. Now, this is the sum total of what each processor actually has to do. They are just doing max shifts worth of shifting. Okay, and they're starting with a sum of 0, and they're adding into that sum the signal times the signal shifted, each element of the signal. Okay, and it's putting that in PP sums, which up here it will be transmitting back to the boss. Okay, here are the points. You're going to do two graphs. One graph of sums versus how much you've shifted, and that will reveal the sine waves. Report the two sine wave periods. The second graph will be a performance graph. You don't have to do pivot tables because we're not doing data set size. We're just doing number of processors, performance versus number of processors, and then comment on that. What patterns are you seeing? One, in the sine wave plot, and two, in the performance. Okay, how is the performance changing when you change number of processors? And that's it. So if we go over here, I was going to show you, I'm not going to run this live because with, you know, with the way things often work, if I run it right now, the cluster will decide to be really busy. So I'm not going to do that, but I will show you what the output was. And this was a bash script, so it was doing one node, two, and this is the minus NP argument on the MPI exec line. Here's 4 processors, 6 and 8. And this is a print statement that's in that do one autocorrelation. You can comment that out if you want. It just kind of pollutes your performance file. But I enjoy watching it because, as you can guess, the scheduling on all these different processors out on the network, there is not necessarily an ordering to them. Okay, surprisingly, this was close. 1, 2, 0, 3. Well, 1 and 2 were in order. 1, 2, 3, 4. Oh, and there's 0. 1, 2. So it came surprisingly close to being in order, and I don't know if that's real or if that's just a coincidence. But number of processors, number of elements, which is constant. Mega autocorrelation, that's my invention of a unit, mega autocorrelations computed per second. And here's what I got, but your mileage will vary. All right, that is project number 7. And of course, if you were working at one of the government labs, we wouldn't stop at, say, 8 processors. We would go up to 8,000 processors and really crank this sucker out. So this should be fun. And it gives you one more tool in your computer scientist tool belt and one more thing to brag about on your resume.